Hi everyone, welcome back to our channel. So today we are going to see electric charges and electric field. Actually this is a one shot video, right? So this is part 1 of it, and let us discuss what are the topics that we are going to deal today. So I'll tell you all the topics that we will talk about before going into the chapter. Okay, so actually this is the first chapter of your NCRT class 12 physics. So let us deal with this chapter in detail today. So before going into that, I'll just show you the contents of what we're going to discuss today. Okay, so we are going to discuss all about introduction. That means we will discuss what is basic things about the charges and what are the things you have to remember for the charges and basic ideas about it. Then we will discuss about Coulomb's law, and this Coulomb's law is very important, right? So we discuss about Coulomb's law. Coulomb's law, you have Coulomb's law in vector form also. That is also important, vector form. Coulomb's law and Coulomb's law in vector form. That also we will discuss. Then superposition principle. We also call it as multiple charges. Multiple charges. That is usually with Coulomb's law you deal only with two charges. So that we study separately about multiple charges. Okay. So in superposition principle, we are going to discuss about multiple charges. Clear? Right. Next up, we're going to talk about electric field. Okay. Electric field you must have heard, right? So like you have heard, I hope you have heard about magnetic field, right? Whenever you place a magnet, so around the magnet for sure magnetic field will be there. We studied about the bar magnet, right? So around a bar magnet, the electric field will be generated. That is usually you have studied about the properties of bar magnet also, how the magnetic field will move. Similarly, here we study about the electric field, and we study about the electric field lines. That means what is electric field and how that electric field lines are generated. And we study about electric flux. Okay, still more topics are there like Gauss law and its application, and some more topics are there like dipole moment that will be discussed in the next session. Okay, all right. So before entering to the session, you have to subscribe to our channel and click the bell icon for notification so that we'll make more videos. So it will be you. Okay. Now we are going to start with the introduction of this chapter. Right. So before starting the chapter, let us see some basic things, right? So imagine you are going in a bus. Okay, imagine you are going in a bus. Okay, so imagine this is you sitting in a bus. Okay, so this person sitting in the bus is you. Okay, so you are traveling to some part of area in your locality, so that you are traveling in a bus. So while you are traveling in a bus, you are sitting in a seat. Initially you are sitting in a seat. Now the bus driver is starting the bus. So what happens? You are going to travel and reach to your required location, right? You're going to reach to your required location wherever it is needed or necessary. Okay, so for example, now you are starting from point A and you have to reach to point B. So your location is starting. So you are sitting on the bus and you are traveling. So while you are traveling, what happened? Your body will automatically go under a jerk, right? Jerk. So due to jerk, what will happen? You will be rubbed with the seat, right? So after all this had happened, your stopping has been arrived. That means you will just get up from the seat and you will hold the rod. At the time, you might have experienced a slight shock, okay, feeling. That is due to what? That is because of what? That is because of what you have observed this shock feeling. Okay, this shock feeling you have experienced because you might have gained some amount of energy or charges, I can say. The best word to use here is charges. You might have gained some charges while you are sitting in the seat. Okay, so while you are going, you might have had so many number of shakes, So that time you might have rubbed with the seed, so that time you might have gained certain charges. And when you touch this rod, this charges you have gained, right? You have gained certain charges. These charges are being released. Okay, these charges are being released. So therefore you observe a shock. Okay, therefore you observe a shock, right? So these are some properties of charges that we are going to learn. So in this chapter we are going to learn about static charges. Static charges. What do you mean by static charges? Static charges means the charges that is going to be placed under rest. That means the charges will move but will not accelerate. That means static charges means no acceleration will be there. Okay, no acceleration will be there. Those type of charges we call it as static charges. So we are going to learn about static charges. Therefore, this unit of chapter 1 and chapter 2 of this lesson belongs to a unit called electrostatics. Electrostatics. So chapter 1 and chapter 2 of this unit belongs to electrostatics. That is nothing but they are going to be the charges without acceleration, right? So what if the charges are accelerating? What do we call them? If the charges are moving from one place to another, what do we call them? We call them as electricity. A beautiful word, electricity, right? So that is why we are getting the fan to be running, right? The light is awning. We can able to use all type of electronic devices. That is because of electricity. When the charges are moving, we can able to observe electricity. Clear? So now we are going to just read about the mechanism where the charges are not accelerating. Clear? Right. So now we will deal in detail, right? We will dive into. See, electric charges are physical properties of matter that can cause them to experience a force, right? So whenever you have electric charges and whenever a force is experienced by electric charge, usually they will experience a force in electric field. But just now you don't need to just think much. We will, while we are discussing the electric field, we will discuss in detail, okay? Now this is important. We all know that there are two types of charges. What are the two types of charges are there for us? See, for example, you take an atom. Okay, I don't, yes, 1 minute. For example, you take an atom, right? Atom. Okay, how does the atom will resemble? How does the atom will look like? See, atom will something look like this. I'm talking about the atom that you read in chemistry, right? So this is how an atom looks like, and the electrons will be moving in this way, and in between you have the combination of protons and neutrons. You all know, right? For you know that always an atom will be neutral in state in their basic form. Okay, so now we are going to take an electron. Electron is negatively charged, and if you're going to check the proton is going to be positively charged. So by nature, in all the substances, you have the two types of charges. One is going to be positive charge and another one is going to be negative charge. Okay, positive charge and negative charge. So usually this one you have to remember, right? Okay. So there is a law of attraction and repulsion. You might have learned in magnetism chapter that same poles will repel and unlike poles will attract. Similarly here, like charges are going to repel. That means positive and positive or negative and negative will repel each other. Okay. And unlike charges, that means you're going to bring the opposite charges like positive and negative that is going to attract each other. These are the basic things, right? Next, electric charges can be transferred from one object to another object by contact or induction, resulting in electrification or charging. So I wanted to tell this. See, what happened when you were sitting on the bus? I told an example over here, right? So you were sitting over a bus and the bus started to move. So you also had certain jerks. Because of that, you have gained certain charges. I used the word gained certain charges. But instead of that word, I can also say a proper word that you have been charged. You have been charged or electrified. Electrified. Okay. So usually when you gain certain charges or when something gains certain charges, we call it as charged or electrified. Clear? So that is what here we are going to talk about. So in detail we'll talk about this conduction, that particular thing, how you can charge a particular substance. There are three methods to charge that we discuss in detail in the future slides. Okay. So electric fields, we discuss about electric fields detail in the next part. So imagine for now, whenever an electric field is there, whenever an electric charge is experiencing certain amount of force, surely the electric field will act on that particular place. This is what you have to remember for now. Whenever an electric charge is experiencing certain force, okay, so then only the charge can be conducted or inducted, whatever you need. If you want to do, certain force should be applied. That force can be an attractive force or a repulsive force. See, this attraction and repulsion itself is a force. This repulsion or attraction itself is a force. That force makes it, right? So electric field will be applied on that particular area where the charges are undergoing a force, right? Electric fields are created by electric charges or changing magnetic field, right? So this is not needed for now. Okay. So but keep in mind, so electric fields are going to be created by electric charges. It can be created by electric charges, like you have electrons, okay, undergoing a certain force. It can create an electric field, that is a negative charge. Or if any proton or positive charge is undergoing any force, then it can create an electric field. And change in magnetic field can also create electric field. Okay. So the direction of the electric field point is the direction of the force that a positive discharge would experience if placed at a point. Okay. So if placed at a point, that would experience the direction of the force. Next, magnitude of the electric field at a point of ratio the force and discharge to the magnitude of the discharge. Okay. So now we'll discuss. Okay. Now I'll discuss. Listen. See, already we have discussed that there are two types of charges. One is going to be the positive charge, another one is going to be the negative charge, right? Already we discussed that there are two charges. One is going to be the positive charge, another one is going to be the negative charge. If it is going to be a positive charge, then we told that it is going to be proton. Then it is negative charge, it is an electron. So usually, what is a charge of an electron? That is very, very important. Charge of an electron. So charge of an electron is 1.6 into 10 power minus 19 Coulomb is the charge of an electron. Then what would be the charge of a proton? So charge of an electron and proton are same. Okay. But here if you put negative symbol, then it is a charge of an electron. Usually we don't represent it. We represent it in modulus. Okay. We don't usually represent negative sign. But both the charges, that is charge of an electron and charge of a proton, are same in case of magnitude. When you take magnitude, okay, when you take magnitude, the charge of electron and charge of the proton are same. There is no certain differences. And one more thing is you have to remember, the charge is a scalar quantity. This is very important. Charge is a scalar quantity. Okay, scalar quantity. So what is all about scalar quantity? We have discussed previously, right? What do you mean by scalar quantity? It does not depend on direction. It only depends on magnitude. So whatever the magnitude you have, it only depends on that. See, charge will not say I will only move in west direction or I'll move only in east direction, right? It moves in any direction. So independent of direction, it moves everywhere. So therefore it is called as a scalar quantity. Right? Scalar quantity. Okay, right. So now these are the basic things that you are supposed to know. And now we are moving on to a very important basic concept again. Okay. So imagine I'm going to take a glass rod. Okay, this is a glass rod. Okay, and I'm going to take a plastic rod. I'm going to take a plastic rod. I'm going to take a glass rod. I'm going to take a plastic rod. Okay, so this is your glass rod and this is your plastic rod. Now, what I'm going to do is, I am going to rub this glass rod with a silk. Imagine this purple color is a silk cloth. Okay, this is a silk. Okay, now I'm going to rub this plastic rod with a fur. I'm going to rub this plastic rod with a fur. Now, what is happening over here? What would you observe? So, you would observe that there is a gain in the positive charge in the glass rod. That is, glass rod will gain positive charge, and there is a change you can able to see where the silk would gain the negative charge all over it. The silk would gain negative charge. That is, charge transfer is taking place here. Charge transfer is taking place over here, where the glass rod got all the positive charge and silk got all negative charge. Usually at the beginning, before rubbing, they are neutral in state. That means equal number of positive charge and equal number of negative charge. But after rubbing the silk cloth and just after rubbing with the glass rod, what happened? The glass rod got all the positive charge to be deposited and the silk got all the negative charge to be deposited in it. Now if you observe this plastic rod, opposite, all the negative charge has been accumulated in the plastic rod and all the positive charge have been accumulated in the fur. So in the condition, if you just observe, silk had got negative charge and glass rod has got positive charge. So the silk has ability to gain negative charge, right? Yes, they can able to gain electrons. That is a meaning. Okay. While I'm rubbing, I got silk with negative charge to be observed, glass rod with positive charge. While rubbing, I observed the fur gaining the positive charge and plastic rod gaining the negative charge. Now, what I'm going to do is, to test it, I'm going to bring two glass rods together. See, when I bring two glass rods together, this glass rod is also positively charged, this glass rod is also positively charged. Therefore, they repel each other and they go away, right? So here repulsion you can able to observe. Now what I am doing is, I am going to bring a plastic rod and a plastic rod near to each other. Since both the plastic rod and plastic rod accumulates the negative charge, so this both are accumulating the negative charge. Okay, negative charge. Therefore, they also repel each other. They also repel each other. Now, I'm going to take another condition where you can able to observe. I'm going to bring the plastic rod and glass rod together. Okay, see, you can able to observe over here clearly that the plastic rod is going to have the negative charge and glass rod is going to have the positive charge. So since they are in opposite charges, what do you know? They will attract each other. They will attract each other. So here what will happen? Attraction will occur. Attraction will occur. Clear? So this is a basic thing, right? This is a basic thing. I'll move to the next. Now we are moving on to conductors and insulators. Very quickly we did with this topic because it's very easy and you all know very well, right? Already. What do you mean by conductors? Conductors are nothing but which readily allows the flow of electrons. Okay, flow of electron is allowed. That is a case called conductor. What do you mean by insulator? Insulator doesn't allow the flow of electrons. The flow of electrons. So example, you can give all the metals. Most of the metals are good conductors. Human body. These can be called as conductors. What are the examples you can give for insulators? Insulators like wood, plastic, okay, plastic, glass. These are all poor conductors of electricity. Therefore, we call it as insulator. Okay. So, if you want to easily remember what you mean by conductor, conductor will call, come on, electron, you can pass on me, like that we'll say. Okay. So that means it will easily allow the electrons to pass through it from one point to another point. Okay. So it is willing the electrons to allow inside it. Okay. Insulator says, no, electron, I don't like you. Don't come near me. Don't pass on me. So I will not allow you to pass. How? Without my permission, you can pass, like that glass. So that is the difference between conductors and insulators. Very simple, right? And one more thing is, so conductors, on the conductors, if you able to observe, always the electrons or the charges that are passing through the conductors will always lie on the surface of the conductor. Will always lie on the surface of the conductor. So whatever the charge you take, the charge on the conductor will be lying on the surface of the conductor. Clear? So these are the things we have to discuss about conductors and insulators. Now moving on to types of charging. Types of charging. Key this word very clearly. So during the first part also, before itself I told no, we will discuss about the types of charging. Here it comes. So we will discuss about the types of charging. There are three types of charging or three methods through which you can charge a particular conductor. You can only charge a conductor, right? Now only we learned. Yes. So three different types you can charge a conductor. So what are the three different types? So the first type is going to be friction or rubbing. The second category is going to be conduction. The third category is going to be induction. Okay, induction. Right. So, this first category called friction or rubbing we have already learned. Where we have learned? You can ask, where we have learned? Yes, we have learned. We have learned previously. Come on, I'll show you where we have learned. We have learned over here. This is a very beautiful example of friction or rubbing, right? So you are rubbing two particles. Okay, under the friction. Friction is a force that opposing, right? You all know very well. So under the friction, you are just rubbing the two particles. Here you are rubbing silk and glass rod. Here you are rubbing fur and plastic rod. Therefore, you are observing the change in charge or charge transfer already, as I told earlier. So this is a very beautiful example of charging through friction or rubbing, right? So we have already discussed about charging through friction or rubbing in detail. So that is what. Okay, that is the experiment that we have done with silk rod and by rubbing the silk rod and silk rod and glass rod. Silk with glass rod, and we have also used what? Silk with glass rod, and we have also used plastic with fur. So this experiment. Now let us deal with conduction. So if I want to tell the difference between these three things, friction or rubbing is nothing but you are doing the physical contact. Okay, complete physical contact between two substances takes place. That means you are taking a particular rod. You're taking a particular rod. With the help of that rod, you are just rubbing that rod, right? You're rubbing that rod. Physically, you're rubbing that rod. But in the conduction, you have to just touch. You have to just touch the end. That's it. You're not going to rub. You're not going to physically contact like that and all. Physical contact is there, but just a touch. That's all. That will happen in conduction. Okay, that will happen in conduction. So let us deal with it in detail. In the next slide, I will teach you. before that I want to teach you about the induction. Okay, what do you mean by induction? Induction means, see, I told this is physical contact. We are just rubbing it nicely so that the charges are performed in friction or rubbing. In conduction, you're just touching it. A slight form of physical touch. That's it. Lightly you're touching the substance. That's it. For induction, what you're going to do is, you're not going to have any contact. Okay, not going to have any contact. Okay, without this, you're going to have contact, but you're not going to have a physical contact. That means you're not going to touch and you're not going to induce the current. Not going to have the physical contact. Physical contact. Like the previous cases, we will not touch the substance itself. Without touching, we will induce the current. That we mean by what? Induction. So let us deal about the friction, conduction and induction in detail now. Okay. So friction we have already dealt. Conduction and induction we will deal with. Okay. Okay. So let us see what you mean by conduction. Okay. Initially I have a pith ball. Okay. Initially I have a pith ball. Okay. Now I'm going to bring the needle and I'm going to just touch it. That's all. So let this needle be negatively charged. So what happens if your pith ball is neutral initially? Come on, predict it. What will happen? Type it in the comments. Type it in the comments. What will happen? What will happen? Yes. This pith ball will become negatively charged. Negatively charged. So this is how you can charge through conduction. Now induction is important. Listen everyone. Listen carefully. Okay. Now induction is very important. So what you are going to do in induction is, we are going to take two different coil. Okay. Adjust with the coil. I'm going to take two different coils. Let me name the coils also. Okay. Let me name the coil. This is coil A and this is coil B. Right. This is coil A and this is coil B. Now I'm going to touch and keep both the coils together. Right. I'm going to touch and keep both the coils together. So let us draw it properly. So let this be coil A, right? Coil A is touched on with, not overlapping. Probably I've drawn something like that. Right. So that's something like this. So both have overlapped with each other. Now both are initially neutral. Okay, both are initially neutral. Now I am going to bring a negative charge from external source. I am bringing a negative charge. So if I bring a negative charge from my external source, what will happen here? So they are neutral charge, means positive charge also present, negative charge also present, but equal in amount. So this side fully, due to attraction, positive charge will be generated. Okay, positive charge will be generated. So this side, what will happen? On the other side, negative charge will be generated. On the other side, negative charge will be getting generated. Now what I am going to do is, I am going to separate these two coils separately. Now I am going to split these two coils separately. Right? Now I have splitted these two coils separately. Okay. So this is now your coil A. Coil A will contain positive charge, will be accumulated on this side, because we have not completely split. So due to attraction, the positive charge is accumulated over here, negative charge is accumulated over here. Now we have not splitted for so much distance. Okay, it's near. So this is coil A and this is coil B. It's near, so that it is accumulated like this. But if I'm going to separate it too far, okay, I'm going to separate it too far. So the charges will be okay, see, it's not too good. 1 minute. So now the charges will be distributed all over. Now this is A, this is B, right? So the charge will be distributed all over. So here all over you will get the positive charge. Here all over you get the negative charge. The charge will be distributed all over. So the step is something like this. First you have taken the neutral AB coil. So this is your first step, and from here we went to here. We have brought an external source of negative charge to this coil. We have touched the two coils together. Now due to attraction, the positive charge is generated over this side. Due to repulsion, the negative charge is secreted over this side. Now this is the second row. Now from here we are splitting these two coils, but they are placed very near to each other, so that the positive charge accumulated this side, negative charge are accumulated over this side due to attraction. Now this one is the fourth one. Now we have separated too far, so that the charges on the coil will be getting equally distributed. Charges on the coil will be equally getting distributed. Clear this one? This is charging by induction. Okay, right. So based on this, they can ask a question also. So in your NCRT, there is a question, something there will be, I hope so, like this only. But the method what I am telling is correct. Okay, but I don't know what charge is given. So they will be telling you that you have to charge the metal plate with positive charge or negative charge. Okay, you have to charge the metal plate with positive charge. For example, this is a plate. Okay, so you have to charge this particular conductor coil with positive charge. If they have told you have to charge only with positive charge. So this particular coil should be charged with positive charge, means what type of rod, charged rod should I bring here? What type of charged rod should I bring here? I need positive charge. That means I should bring the opposite negative charge. I should bring the opposite negatively charged plate I should bring, or charged rod I should bring. So due to this, what happens? The positive charge will be collected at this end and negative charge will be collected at this end. Now according to the question, they have asked me to collect the positive charge. That means the negative charge can be removed by grounding. What do you mean by grounding? Sending the charges, extra charges to the earth surface. So usually this grounding setup can be seen in our houses. Okay, usually it will be there in our houses. That is, you have three types of wire, right? Live wire, fuse wire. So if any extra current are passing through the wire, it will be directly moving to the ground, so that it prevents appliances and us also. Right? So this is what. Okay. Are you clear? Now moving on to the next concept. Basic properties of electric charges. So when you want to discuss about the basic properties of electric charges, there are three basic properties of electric charges that I have to discuss with you about. First one is additive of charges. First one is additive of charges. Right? Additive of charges. What do you mean by additive of charges? Very simple concept is one. Just nothing but you're having a collection of charges. For example, this is a surface, okay, where you have different charges, -5, +2, 3, +3, -8, +5, okay, +6, like that. You have so many charges. So what is the total charge present in this system? That is the additive charge. You add all the charges. For example, 5 charges are present: Q1, Q2, Q3, Q4, Q5. Means you will add all the charges as Q1 plus Q2 plus Q3 plus Q4 plus Q5. You will add all the charges. And if I want to tell that when you add all the charges, you should add with the sign. That is very important. You should add with the sign. So for example, you take this particular system so that you will observe it very cleanly. Let this be Q1, Q2, Q3, Q4, Q5, Q6. 6 charges we have. So Q1 is 5 minus 5. You have to substitute with the sign. Q2 is plus 6. Q3 is plus 3. Q4 is plus 5. Q5 is minus 8. Q6 is plus 2. So with the sign you have to substitute, and if you solve this particular equation you get the additive of charges. Okay, now that's not needed. We have to go quickly. Okay, now next property is, that's all additive of charges. Okay, next property is charge is conserved. Charge is conserved. What do you mean by charge is conserved? See, already we have studied in our lower classes that the charge or anything, okay, a reaction or charge, it can be neither created nor be destroyed. Okay, so that means it will only get conserved. Okay, it will change. It can change from one form to another form. Okay, it can change from one form to another form. But see, you have kinetic energy, it can be converted to potential energy. Okay, so the charges can change its form from one form to another form, but it cannot be created or destroyed. So the total charge in the system will always be conserved. This is the second property that we are going to discuss. And now I'll discuss the third property. So your third property is going to be nothing but a very important property, quantization of charges. Quantization of charges, very important property. So what is all about quantization of charges? Quantization of charges means Q is equal to Ne. So what is your Q is equal to Ne? Q is nothing but the charge of the electron. N is the integral multiple. Always the quantization of charge should be an integral multiple. So N is an integral multiple where N can't be a fraction or decimal. N should be always an integer. That means N can be equal to plus or minus 1, 2, 3, 4, 5 and so on. Okay, N can only be an integer. Okay, and Q is a charge of an electron or charge of the particular electron that we are taking here, number of electrons. E is the charge of a single electron. And we have already mentioned the charge of the single electron is going to be equal to 1.6 into 10 power minus 19 Coulomb, based on that only, right? Charge of single electron will be 1.6 into 10 power minus 19 Coulomb. Clear? Right. Now we came into a very important session, right? Very important topic. So Coulomb's law. So what does Coulomb's law states? So we no need to go with all these points. Very important, I'll tell you. So Coulomb's law applies only for a 2-point charges. Only if you have 2-point charges, then only you can apply the Coulomb's law. Okay. Okay, the point charge. What do you mean by point charge? Point charge means if you take two charges, Q1 and Q2, the distance between them are the radius of Q1 or Q2 should be less than the distance R. Can you able to understand? See, if this is a charge Q1, okay, this has certain radius capital R, and you are placing the another charge Q2, for example, okay, the distance between them is smaller. That means your small r should be greater than capital R. Then we call it as a point charge. Very small sized charge. Okay. Okay, it's a very small sized charge compared to the distance between them. Okay, compared to the distance between the charges. That is what I told you now, right? So, this is a very important thing for a Coulomb's law. So, the statement I have given in the previous slide, if you want, you can copy. Now, I am going to tell the mathematical expression of Coulomb's law. So, after expressing the mathematical expression, you can able to clearly understand what you mean by Coulomb's law. Then we will read the definition. So, it states that your force is directly proportional to the product of charges, that is Q1 and Q2. Okay, that is nothing but you have two charges. Okay, let me consider you have two charges, that may be a positive charge or negative charge. Okay, the force created between them can be an attractive force or repulsive force. Whenever you have two different types of charges, there happens the Newton's law, the Coulomb's law, sorry, Coulomb's law. Okay, there happens Coulomb's law. So what happens is, this is positive charge and this is negative charge. Now attraction will take place on the either side. So force will act on the opposite side. So this is force of attraction. If I took two negative charges or positive charge, force of repulsion will take place. No problem. So this is R. Let this be Q1 and let this be Q2. So based on this diagram, what I can say is, I can say that your force is directly proportional to Q1 and Q2. So force is inversely proportional to the square of distance between them. See, if the distance increases, surely logically you think force will be acting upon the less area. So if you increase the area, the force will be very much feeling difficult to act. So I am going to take this as second equation. So from 1 and 2, you can able to observe that your LHS is same, therefore your RHS will also be same. F is directly proportional to Q1 Q2 by R square. To remove the proportionality symbol, you should introduce a proportionality constant. Here the proportionality constant is K. K Q1 Q2 by R square. So K is nothing but, you have the value for K 1 by 4 pi epsilon naught into Q1 Q2 by R square. Right? This is your force. Okay, this is your force. So this is how you would represent your force. Okay. K also you can represent, no problem. So now listen. Now if you read, it will be easy for you. That's it. We have completed. So the force between two point of charges is directly proportional to the product of their magnitudes. That is nothing but the charges over here, charges, and inversely proportional to the square of the distance between them. Inversely proportional to the square of the distance between them. Right? Very simply we have completed. Next up. The force acts along the line joining the charges and has the same direction as the electric field due to the source charge. Since it is a source charge, where the direction the charges acting, no, it acts in the same direction of the electric field. So force, F is a force, K is a constant, Q1 and Q2 are the charges, R is the distance between them. We have discussed that, right? And one more thing is the value of K. The value of K is 9 into 10 power 9 Newton meter square per Coulomb square. The value of K is nothing but, if I want to write it more clearly, I'll write on the top so that you can note it down. So this is very important for calculation purpose. You should remember this value. Okay. So your K is equal to 9 into 10 power 9 Newton meter square per Coulomb square. This is the value of your K. This is the value of your K. Right? Remember this. So this is important. Okay. Then what is the unit of force? Unit of force is Newton. Okay. Unit of force is Newton. And what is the unit of charge? Unit of charge is Coulomb. We already know it very well. Right? Unit of charge is Coulomb. Now moving on to vector form. So how do we do a vector form? So for vector form, I'm going to consider a point O. First, listen the diagram very carefully how I'm drawing. So let me consider a point Q1 and Q2. Always Coulomb's law applies between two charges. So from external source, I'm connecting this, right? From an external source, I'm connecting this. So let the distance. So the distance between Q1 and O can be R1 and Q2 and O can be R2. Now what I'm going to say is that Q1 is going to exhibit the force where Q2 is going to act on Q1 causing the force F12. Okay. And Q1 is going to act on Q2 causing a force F21. So the distance between them can be written as R21. In vector form I am writing, that is nothing but R2 minus R1. Right. Now this one is enough. all are in vectors because we are representing in vector form. Now we are going to start the derivation. Okay, we are going to start the derivation. See, very simple derivation only. What do you mean by F12? F12 is nothing but force of 2 acting on 1. F12 means force of 2 on 1. F21 is nothing but force of 1 on 2. Right? That is the meaning. Okay, that is the meaning. Now what I am going to tell is, see, your F12 vector is equal to 1 by 4 pi epsilon. Already we know what is the value of force, right? Q1 Q2 by R12 the whole square into R12 cap. So to represent in the vector form, you should mention it with unit vector. F21 is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R21 square into R21 cap. Now if you just observe these two equations, okay, the magnitude are same. Am I right? Their magnitude is same. Magnitude is same. Okay, but they vary in direction. So if your F12 is acting on this direction, your F21 will act on this direction. That means they are acting on opposite directions. If one is acting on this direction, another one is acting on the opposite direction. That means the direction varies, but their magnitude is same. So you can say that they are going to obey the Newton's third law. Newton's third law they are going to obey. That means you can say your F12 is equal to minus of F21. Can we say? Because their magnitude is same, they are moving in opposite directions. That means you can say they are going to obey Newton's third law, right? Okay, very well, well done. Now we are going to move on to the next concept. Next concept is superposition principle. Interesting, right? Yes, superposition principle. Simple. See, you had multiple charges. There is only two charges. We discussed about only two charges, where one charge is going to act on the another charge, another charge is going to act on this charge. They are interdependent. But here, see, you have many charges. One charge, okay, will going to act on many charges. Let Q1 be one charge that is acting on Q2, Q3, Q4, okay, Q5. Like that, you have n number of charges. Qn, like that, you have n number of charges it is acting on. Then how can you just write the equation, or how can you derive it? So I am going to take F12. You know the meaning, what do you mean by F12? Force on 1 acted by 2. Right? You know what is the meaning of F12. So that, what do you mean by F12? What will be F12? 1 by 4 pi epsilon naught Q1 Q2 by R12 whole square into R12 cap. Here you don't need to mention cap, but also you mention vector form itself. Okay. Then F12 is over. I am going to now take F13, because see, you have to take 1 for all the values, because 2 is acting on 1, 2 is going to act on 1, 3 is going to act on 1, 4 is going to act on 1, 5 also. Everything acts on 1, therefore everywhere you should take 1. 1 by 4 pi epsilon naught Q1 Q3 by R13 the whole square into R13 cap. Clear? So this is how you will get your second equation. So like that you can write for F1n, till F1n you can write the equation. So F1n means how you will write? 1 by 4 pi epsilon naught Q1 Qn by R1n the whole square into R1n cap. Like that you can write for R1n. That means you can write for how many ever charges that are present. Now you have to get the total force. To get the total force, what you will do? You will add all the force, right? To get the net force, you have to add F1, F12 plus F13 plus till you have to add it till F1n. Okay. In order to get the net force, you have to add all the forces that are being there. That means you should add 1 by 4 pi epsilon naught into there is Q1, Q2 by R12 the whole square plus 1 by 4 pi epsilon naught into Q1, Q3 by R13 the whole square. Like that you have to add till uh, 1 by 4 pi epsilon naught Q1, Qn by R1n the whole square. Okay, like that you have to add for all the values. Okay, so now we are adding all the values. How to mention it in the very simplest form? How to mention it in the very simplest form? If you need, you can take the vector also. Here R12 cap. Here you have R13 cap. Here you have R1n cap. Take the vector also. Okay. Now, how to mention it in the very simplest form? Okay, I'll just write it over here so that will be visible, right? I'll write it over here. Okay, so how to write it in the very simplest form? So your F net will be equal to, see, Q by 4 pi epsilon naught. So 1 by 4 pi epsilon naught is common actually for all 1 by 4 pi epsilon naught. And if you just see means Q1 is also common. Q1 is also common everywhere. So can you take Q1 common outside? Q1 common outside. So Q1 by 4 pi epsilon naught. I am taking common outside. Okay. And now I am going to do summation of. Okay. Your I should start from what value? Tell me your I should start from what value? Your I should start from 2. Your I should start from 2 only. And your I can be up to n. Your I should start from 2. It can be up to n. So, another one charge is there, no? That I am going to mention it as Qi by R1I whole square into R1I cap. Okay, R1I cap. Clear? R1I cap. So, right? So this is how you will represent the net force. So this I can be applicable from 2 to n, whatever the values you applicable, apply over here, you will get the answer. Okay. So this is what you mean by superposition principle. Clear? Clear? Now moving on to the next. Next is we are going to talk about dielectric constant. It's very simple concept. Okay. So dielectric constant is nothing but your K is your dielectric constant. Dielectric constant is nothing but force on vacuum by force on medium. So your in your epsilon naught is permittivity of the permittivity. You have epsilon and epsilon naught. If you take epsilon naught, it is permittivity in case of vacuum. Okay, it is permittivity in case of vacuum. It is permittivity in case of medium, right? So force 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught in vacuum, 1 by 4 pi epsilon in medium. Usually the force you will be writing it as like this, right? If you divide, automatically these two terms will be getting divided, and this particular thing will also be getting divided. Now what you will have is, you will have 1 by epsilon into 1 by epsilon naught can be written as epsilon by epsilon naught. This is your force vacuum per force medium. So you will finally get here 1 you will have here 1, sorry, here you guys will have 1. So that means your force per vacuum by force per medium will be equal to epsilon by epsilon naught. So this one can be written as K. K is equal to epsilon by epsilon naught. So your K is nothing but your K is your dielectric constant. Clear? Clear? Any doubt? Right. Now moving on to the next concept. So one part of the session we have successfully completed. Now moving on to the next part of the session. See, next part of the session is very important again. Okay. One part of the important session we have completed. Congratulations for you all for attending this session continuously. So keep on continuing this session. You will be getting motivated, right? So by the end of this session, you will be clear with what you mean by Coulomb's law, how to derive Coulomb's law in vector form, how to derive Coulomb's law in normal form, electric field, okay, all that. Now moving on to the next part of the session, electric field, right? Electric field. Now till now we have discussed about, see, whenever a charge is applied, whenever a force is applied on a charge, electric field will be created. This is what we have discussed previously, right? Whenever a charge is there and whenever you apply a force, there always electric field will be created. Yes, of course, it is true. So electric field will be created when you apply a force. It is a region around a charged object where another charged object experiences a force. So whenever an object experiences a force, there created a electric field. Electric field is a space around which the charge is experiencing that particular force. We call it as electric field. Okay. So electric field intensity at any point is defined as a force per unit of positive charge placed over that point. Yes, you can understand, right? So unit of electric field intensity is Newton per Coulomb. So unit of electric field is given. Unit of electric field is Newton per Coulomb or volt per meter. See, both these units you have to remember it very well because they can give in MCQ type of questions and all. They can give you, okay, write the SI unit of electric field they can give you, and they in the option, okay, they will give you the question, write the SI unit of electric field. In the option they will give you Newton inverse meter inverse, okay, B Newton per Coulomb, C Newton meter per Coulomb, okay, D meter square. Like this they will give you. So what option do you select? You select B option. Of course I know you will select B option, but what you will do now, you always will learn only this particular unit. Okay, if they change and ask this particular unit means you guys will not answer. Oh no, whatever I have learned is not there. What is this? What hell is this? How can I answer? So don't worry, from now you learn this. Okay, volt per meter is also one of the SI unit of electric field, right? So they can ask volt per meter also. So if they ask, you can write now, right? Yes. The direction of electric field intensity is same as the direction of the force on a positive test charge. Okay, so that we have already learned, right? So next up. Okay, the electric charge due to a system of charge is obtained by the principle of superposition. Okay, right. So it states that the net electric field at any point is a vector sum of the electric field intensities that arises due to a individual point. Okay, right. Now, if I want to talk about the electric field for easier purposes. Okay, so electric field, if I have to tell you more, it is the force. It is a force that is acting per unit charge. It is force that acting per unit positive charge. That means you will tell your test charge to be as a positive charge. Test charge has to be as a positive charge. So you can tell that your E is equal to F by Q naught. Okay. So electric field is nothing but the force per unit positive charge. Your test charge will always be positive charge. So here instead of putting Q, I'll put Q naught. That is nothing but your test charge. Okay, test charge. I'll put Q naught. Clear? Okay. Now your test charge will always be positive. This is a expansion you have to write. It's a vector form, right? Electric field is a vector form and force is also a vector form. So you can represent it. So electric field is a vector. Okay, vector. So we have discussed the SI unit of electric field. So SI unit of electric field can be Newton per Coulomb or it can also be volt per meter. Don't get confused. It can be Newton per Coulomb or volt per meter. Okay, both if asked in examination you are supposed to write. Okay, right. Now moving on to the very important concept, electric field due to a point charge. So we will start with electric field due to a point charge. See, this electric field due to a point charge is an important derivation. So listen carefully, okay? Very simple, easy derivation. So listen. So electric field due to a point charge. Now how can you find an electric field due to a point charge? Now listen. We are going to have two charges, right? This is a source charge. Let this be Q, right? Placed on the position O. Okay, and somewhere around the position A, I am placing the test charge, and now the force is acting on this direction. Okay, force is acting on this direction, right? Now this is your source charge and this is your test charge. Any doubt over here? Source charge and test charge. Now listen carefully. What do you know the formula for your electric field? You know that your electric field is equal to nothing but force acting upon unit charge, right? Electric field, you know that it's nothing but force acting upon a unit charge. That means first I will write the force formula. What is the force formula? Force formula is nothing but, you are going to talk about the electric field due to a point charge. That means you need only one charge. I am going to consider only one charge, right? So force is equal to 1 by 4 pi epsilon naught. Here two charges are there, q naught by r square, right? The distance between them, let it be r. The distance between them is r, right? R square. So now this is your force. Let this be the first equation, and charge is q naught itself. So now your electric field will be equal to force. This particular value I'll write 1 by 4 pi epsilon naught into q naught by r square. I have to divide the entire term by q naught. So I am just writing here q naught because I am dividing the entire term by q naught or writing here is same. So this q naught and this q naught will be getting cancelled. So your electric field you will get it as 1 by 4 pi epsilon naught into q by r square. Right? So this can also be written as your electric field is nothing but equal to q by this, instead of this particular value I can write kq by r square. Kq by r square. Vector representation, r cap you should put for vector representation. Okay. Now if I am going to draw a particular graph based on the electric field and the distance, let this be the electric field and this be the distance graph. Okay, let this be the distance graph, r square. So always the distance will, if increase in distance will decrease the electric field. Increase in distance will decrease the electric field, right? And if you just observe this equation, the electric field does not depend on this point charge. It only depends on the source charge. This is a very important observation over here. Electric field do not depend on test charge, right? It only depends on the source charge. You have source charge, so it only depends on the source charge. It does not depend on the test charge. This is very important observation. Okay. Now moving on to the next, electric field due to a system of charge. So electric field we have studied for only for a point charge. That means only for one charge we have just studied. System of charges means many charges we are going to have, and we are going to study about many charges. Okay, many charges. So let me consider the axis. Okay, let me consider two axes. It's not coming proper. Okay, let me draw two axes. Adjust with me. Okay, two axes. Let this be the x-axis and this be the y-axis. Right. So I'm going to have two charges. Let this be q1 and q2 on the axis. So from the origin, right, you just draw the line joining this. Okay, joining this. Right. So now what I'm going to do is I'm going to extend this. I'm going to extend this. So this is the way my electric field acts. If I extend this, this is the way my electric field acts. Electric field of one acts, electric field of two acts. So you know that the vector sum whenever you are taking, that will be nothing but you are taking the vector sum. So this one will be E1 plus E2. Okay, E1 plus E2. Now the distance I am going to tell it as R1 distance. I am going to tell this as R2 distance. Now we have multiple charges. Okay, system of charges means some particular charges you have, right? So electric field caused due to the first charge, that is what I need. You already know the formula, 1 by 4 pi epsilon naught into only one charge will be acting, q1 by r1 square. Here I can write it as r1 p square. Going to take some particular constant. Okay, r1 p square into r1 p cap. Right, you're going to take just certain constant over here, p, right? So usually we take 2 in vector form. Usually we take 2 in vector form 2. So like that we are taking 1p. Okay. Okay. E2. E2 will be what? 1 by 4 pi epsilon naught into Q2 by R1 R2p whole square into R2p cap. Right. So like this you can write for till En, you can write till how many ever the charges you have, you can write for that many ever charges, till n number of charges you can write. Okay, so now your E net, if you need, you will just add E1 plus E2 plus how many ever the charges are there, that many ever charges you will add. So that can be written in simple ways like your E vector is equal to 1 by 4 pi epsilon naught is common. So take 1 by 4 pi epsilon naught common. Summation of, here your I belonging to 1. From 1 itself is starting, no, it's changing charges. And it is ending at n. So Q I by R I P whole square into R I P cap. So this is what you supposed to write. So this is your electric field due to a system of charges, right? Electric field due to a system of charges. Clear? Clear? Any doubt? So you should not write only the derivation. Before the derivation, you should explain what are the things. As I told, no, in wordings, whatever I have told in wordings, that should be written as a wording. Okay, whatever I told, you should be writing it as wordings in your exam sheet. Okay, okay, right. So clear with this concept, right? Now moving on to the very important concept. Okay, so before going on to that concept, I would like to teach you one thing. Okay, I would like to teach you one thing. There is nothing but, see, see. Okay, we'll move on to that particular concept now. Okay. Electric field lines. So one of the very important concept, electric field lines. From here, what type of question you can expect is, from here diagram based question you can expect. From here diagram based question you can expect. Okay, diagram based question in the sense, you can expect to draw they will give you certain conditions, you have to draw the electric field lines based on it. Okay, in that way, or they will give you the diagram and they will ask what type of charge it is, like that. Okay, right. So electric field lines are nothing but they are the graphical representation of electric field. So you know that whenever a charge is there, force will be applied. If force is applied, electric field will be generated. This is the thing we already know. So if electric field is generated, surely electric field will apply only to certain boundary or certain minimum extent. So to show it graphically, to show it representatively, how the electric field is acting, we use electric field lines. So electric field lines are graphical representation of electric field. They are drawn such that start from positive charge and end at the negative charge. These are some of the properties of the electric field. These are the properties of electric field. So your electric field, it should start from positive charge and it should end at negative charge. It only should move from positive charge to negative charge, right? If it is at if only one charge is present, then the electric field will move up to infinity. The electric field will move up to infinity. They are tangent to the electric field intensity at any point. Whenever you take any point you take, they should be tangent. They never cross each other. Already we know what happens if they cross each other. They will show two different types of properties and that is not at all possible. Okay. So single charge move up to infinity. That is what I told, right? Right. Now let us see the diagrams. Okay. Let us see the diagrams. So diagrams based on the positive charge. Positive charge. So positive charge they will not directly give. They can also give it as draw the diagram for Q is greater than 0. If your Q is greater than 0, then it is surely a positive charge. So you would show the positive charge. I need some more space. Right. So you show the Q positive charge and you show this direction. Something like this you should draw. Okay. And you should show radially outwards. So always your positive charge will move radially outwards. This is very, very important. Important note. You write as note. Write it as note. Note. So positive charge will always move radially. Will always move radially outwards. Okay, this is very important observation. Positive charge will always move radially outwards. Next, you are asked to draw the negative charge. So if you are asked to draw the negative charge, they can also tell Q is less than 0. That means it's negative charge. So you have to draw the similar way, okay, for negative charge. But it comes inside. You show the arrow marks that is going inside. Something like this. So here the point you have to write is negative charge will move radially inwards. Clear? That's it. Now moving on to the next, you should draw some more diagrams. What if it moves from positive to negative? What if it moves from positive to negative? If it moves, what happens? Okay, so right, you draw the diagram for that. So I'm going to take the positive charge. I'm going to take the negative charge. You know that. So from positive charge to negative charge, if it goes, you have learned the property. So always the charge will move from positive to negative. And here also some charges will be generated. Okay, here also some charges will be generated. Electric field will be generated. So for positive charge, it moves radially outwards. For positive charge, it moves radially outwards. Therefore, like this. For negative charge, it moves radially inwards. Therefore, like this. Clear? Okay. So, for example, now you take two different types of slabs. You take two different types of slabs. This is a positive slab. Okay, positive rod. How the electric field will act? Like this. It will move radially outwards. So if you're going to have the negatively charged rod, then it is going to move radially inwards. Very simple concept. So you have to just understand it when it moves radially outwards and when it moves radially inwards. Clear? Clear with this? So we have completed the electric field lines, right? So now we are moving on to charge distribution. Charge distribution is, see, listen carefully for charge distribution. You have three different kinds of charge distribution. First one is going to be, one second. First one is going to be linear charge distribution. Linear, I'll write it as CD, okay? Better for us, for convenience. So first one is linear charge density, linear charge distribution, and second one is surface charge distribution. Surface charge distribution, and the third one is volume charge distribution. Volume charge distribution. So now let us deal with each and everything in detail. Now first let me deal with linear charge distribution. First of all, what do you mean by linear? Linear means what? Linear means something in one dimension, we call it as linear. Something in one dimension, we call it as linear. Something in two dimension, we call it as surface. Area we say. Area we find out for two dimensional figures. For two dimensional figures, we find area, right? Surface area. Next, for three dimensional image, for the three dimensional object only, we find the volume. So volume charge distribution is for 3D, surface charge distribution is for 2D, linear charge distribution is for 1D. That means dimension I have mentioned. Now I'm going to talk about linear charge distribution. Linear charge distribution. So for linear charge distribution, I'm going to take a linear source, like I'm going to take a wire or something else. So something like this, my wire is. So my wire is completely of positively charged wire I took. Okay, this is my wire. Let me consider a small length dl, okay, with which I'm going to perform this. So linear charge distribution is nothing but the charge that is distributed along the length. So that can be told, that can be, you can tell it as charge per unit length. Charge per unit length. Okay, so that is the meaning of linear charge distribution. So linear charge distribution means, see how much ever the charge is distributed along the length. That is called as linear charge distribution. So linear charge distribution is always represented with lambda, right? So you will write lambda is equal to, you take the small length, so you will take a small charge. So charge per unit length, right? Charge per unit length. So what is the SI unit will be there? Charge is Coulomb, length is meter. Charge is Coulomb and length is meter. So you will get Coulomb per meter is the SI unit of linear charge distribution. Now moving on to the next, we are going to talk about the second type, that is surface charge distribution. Okay, surface charge distribution. As I told earlier, the surface charge distribution is for two dimension, right? So two dimension, I'm going to draw the diagram as two dimension diagram. So two dimension diagram I'm going to draw. Listen here. See how I'm drawing. So like this, something like this, I'm going to draw it. Okay. So here completely charges are filled. So this is how you can draw the diagram, right? So inside a particular confined area, if the charges are filled, we call it as surface charge distribution. So your surface charge distribution is usually represented with the symbol sigma. Okay. So what you can say about surface charge distribution? It is a charge per unit area. It is the charge per unit area. Okay, it is a charge per unit area. That means your sigma will be equal to, see, I'm going to take a short area. That means charge per unit area in the sense dq by dA. So this is your charge per unit area. I'm going to take a small area. I'm going to consider a small area. Imagine I'm just considering this particular area. So if I consider a small area, then we are going to take your sigma is equal to dq by dA. Clear? Now the SI unit of it will be Coulomb per meter square. Coulomb per meter square. This is the SI unit of surface charge distribution. Okay, Coulomb per meter square. Okay, so surface charge distribution is charge per unit area. Now moving on to volume charge distribution. Okay, moving on to third type, volume charge distribution. So what do you mean by volume charge distribution? So let us see now. See, for example, now we are going to talk about, see, what do you mean by an electric flux? We have discussed. So for certain area, it is the electric field. If it is passing, then it is called as an electric flux. So we have defined it word by word. By writing it in words, we have expressed. But we have to express mathematically. How do you say it mathematically? There is nothing but your flux. That is your electric flux is, or I can say the electric flux, that is, I'm going to take a minimal electric flux. Okay, small electric flux that can be equal to how much amount of electric field passing through it into unit area through which it passes. So small area, let us take it as ds. Okay, now what I'm going to do is, see, this one is going to be an dot product. That means I can expand it, right? So if it is a dot product, then you will get eds, cos theta, correct? If it's a dot product, then you will use cos theta. If it is a dot product, you use cos theta. If it is a cross product, you use sin theta, right? You remember. Now if theta is equal to 0 degree, okay, you get your flux is equal to eds, which is going to be maximum. If your theta is equal to 90 degree, your flux is equal to 0. That means it is minimum value. And one more thing I wanted to tell you. See, your electric field strength. So your electric field strength means how much extent it will be. That is directly proportional to the density of field lines. See, suppose you are having the electric field. This is an electric field. Okay, and you have another electric field. This is an electric field. Okay, so which electric field will have more strength? Which electric field will have more strength? Of course, this will have more strength. Okay, because the density of this is more. Density means thickness, right? So density of this field line is more, therefore it will be more stronger, right? So the thing I'm going to write is very, very important for 1 mark purpose. Okay. So for 1 mark purpose, whatever I'm going to write now is going to be important. Okay. So I can say that if the field line is more denser, then it is going to be more stronger field will be emitted. Stronger field will be emitted. If it is going to be less denser, then less field is going to be exhibited. Okay, dears? Okay. Now we will move to the next. So I'll give you a question over here, very very simple question. Now based on what we studied. So this is one field line that we have. Okay, this is another field line that we have. Let this be A. I'm not writing over here. Okay, and you have another field line over here. Okay, you have another field line over here. Okay, right. So now let me name it. Okay, let me name it. Let me name it. So this is your A, this is your B, this is your C. Now tell me which all are electric fields representing an electric field line, electric field lines. Tell me which line will be more stronger and which line will be more weaker as well. More weaker as well. So you have to tell me in the comments now, right now. So which will have more stronger field lines and which will have more weaker field strength. Field strength will be stronger for what? Field strength will be weaker for what? Come on, tell me quickly in the comments. I'm going to see now. Quickly tell me. So mention like if A or B or C, like that. Which one is your option? You mention that, and after mentioning the option, put it as stronger or weaker. Okay, after putting the option, tell it stronger or weaker. Come on, quickly, quickly. Very good, I get more responses. Very good, very good. So now A, B, C is there. So which one is more denser? This one is more denser. Which one is more lighter? This one is more lighter, right? So which one is lighter will have the weaker field strength. So your C is going to be having the weaker field strength, and your A is denser, therefore it is going to have stronger wavelengths, right? So stronger electric field, so therefore your A will have stronger. So those who have said A and C, A for stronger and C for weaker, congratulations. Right guys, so if you just see here the SI unit of electric flux, the SI unit of electric flux you have to tell. Okay, this is a great task, right? So you have to tell me the SI unit of electric flux. Already I told the formula for electric flux, that is your flux is equal to, that is of course electric field into ds into cos theta. So with the help of this, predict the SI unit of electric flux. Tell me quickly in the comment area. So tell me quickly in the comments. Come on, tell me. Now itself you have to tell whether it is A option or B option or C option, whatever. Tell me now quickly. So what could be the possible options that you can have? Very good, very good, very good. Those who have predicted correctly, very good, and a great round of applause for you all. Okay, great. Correct option is option D. I have not told what is the SI unit of electric flux, right? So one day I ask this question. Based on that, you can predict, no? So the SI unit of electric flux is option D. Okay, so Newton Coulomb inverse meter square, that can be written as Newton meter square per Coulomb also. Okay, both are same. Okay, so with this I'm ending the session, and thank you so much for watching this video. And if you like this video and if you think you have gained some knowledge from this video, right? So we have discussed so many things in this video. Okay, so we have discussed about nearly half of the chapter. We have completed nearly 50% of the total chapter in this video, and I have also told which are the important concepts you have to concentrate while learning. So now itself go, after completion of the session, just learn those concepts. I told what are the concepts I told today. It is very very important. superposition principle I told point charge. No, point charge we discussed. Point charge. Okay, electric field due to a point charge. That go and discuss it today. And electric flux. These are very important concepts. So discuss it and practice it for the fullest. Okay, so and rest of the chapter we have axial point dipole moment, dipole at axial, dipole at equatorial, and we have to discuss about Gauss law and its applications. All sorts of applications we have to discuss, and there will be a separate video for solving all the numericals. Okay, we will solve more number of numericals, that you will be clear with this concept and clear with this lesson. So thank you so much for watching this video. Kindly subscribe to our channel and click the bell icon for notification. And kindly like this video. If you like it, hit the like button. Smash the like button like something. And finally, thank you so much. Bye.